Welcome back to the Quarterly Call. All content is for informational purposes and is not investment advice. Please consult with an investment professional.
Right. Definitely keep that in mind as we get into this.
Yeah, absolutely. So right now, literally as you are listening to this deep dive, there are these specialized Boeing 747s crossing the Pacific Ocean.
The massive cargo ones, yeah.
Exactly. And they are carrying individual pieces of manufacturing equipment that weigh like over 200 tons each.
It's just wild to even picture that.
It is. And these machines cost hundreds of millions of dollars apiece. They're landing, and then these massive things are being trucked straight into the Arizona desert.
Right into the sand?
Yeah, literally into the desert. To be installed in these facilities that are so incredibly complex, the clean rooms are purer than the vacuum of space.
Which is just a crazy metric when you think about it.
It really is. And all of this logistical insanity, this multi-billion-dollar migration of heavy industry is happening for one very specific reason.
Right, because the old cycle is over.
Exactly. The smartphone cycle. I mean, that was the engine of the global tech economy for, the last 15 years?
At least, yeah.
But it's effectively dead as a growth driver now. It has been entirely replaced by autonomous AI agents. So today, we are taking a deep dive into the mid-2026 strategic and financial update from Taiwan's semiconductor manufacturing company.
Better known as TSMC.
Right. The invisible scaffolding of the modern world.
That's a great way to put it, honestly. And the scale of what we are analyzing today is, well, it's difficult to overstate.
So what's the goal for the listener today?
Yeah, so your mission as you listen to this conversation is really to just grasp the sheer incomprehensible magnitude of this shift.
The AI-driven structural shift, right?
Exactly. It's completely reorganizing global manufacturing. We're going to look at why hundreds of billions of dollars are literally being buried in the desert sand.
Which sounds like a terrible investment when you say it like that, but...
Right, but there's a huge reason for it. We'll also cover how artificial intelligence is permanently rewriting the laws of hardware engineering. Oh, the physics stuff. I love that part.
Yeah, the physics are hitting a wall. And finally, we'll talk about what the physical constraints of computing will actually look like as we approach 2029.
Because we are definitely moving past the theoretical phase of AI, right? Like the chatbot phase.
Oh, absolutely. We are deep into the brutal physical reality of building its infrastructure now.
And the numbers in this mid-2026 update, they reflect that physical reality perfectly. And they are, frankly, shocking.
They really are. I mean, the revenue alone...
Let's get into that. So the second quarter closed out with $14.2 billion in revenue.
Which hit the absolute high end of their guidance.
Right. But the guidance they issued for the third quarter is what caused this massive reevaluation across the whole sector.
Yeah, people lost their minds over this.
They are projecting Q3 revenue to land somewhere between $44.6 billion and $45.8 billion.
Which is just... I mean, that's a 37% year-over-year increase.
For a company that was already one of the largest on Earth? Right. You don't usually see that kind of hyper-growth at that scale.
No, you don't. And when you dig into the composition of that revenue, you realize that tectonic plates of the technology sector have just completely shifted.
That internal breakdown of the revenue is, I think, the most critical data point in this entire update.
Break it down for us, because it used to be all about the phone, right?
Exactly. Historically, the smartphone dictated the entire rhythm of the semiconductor supply chain.
Like Apple or whoever announces a phone and everything moves around that.
Right. The annual release of those flagship consumer devices funded the research, it drove the capital expenditure, and it set the manufacturing timelines.
But not anymore.
Not even close. Look at this recent breakdown. High-performance computing, or HPC, now accounts for 66% of their total revenue.
66%?
Yes, and that segment alone grew 20% sequentially just from the previous quarter.
That is massive. And what about smartphones now?
Smartphones have shrunk to just 22%.
Wow. From being the main driver to a fraction?
Right. And then you have the Internet of Things sitting at 5%, automotive is at 4%, and traditional data center equipment.
You mean like the legacy networking gear?
Yeah, the old traditional server stuff. That is effectively a rounding error now at 1%.
That's crazy.
And if you look at the nodes, the advanced technologies, meaning the 7-nanometer process nodes and below, they now make up 77% of all wafer revenue.
So the entire center of gravity has just shifted to the absolute bleeding edge of physics.
Precisely.
I mean, we always knew AI was going to require immense compute. Everyone saw that coming.
Sure.
But the speed of this transition from consumer electronics to HPC is staggering. It's like, I was thinking about it like a locomotive.
But how so?
Like if smartphones were the old steam locomotive pulling the entire semiconductor train for the last decade,
Right.
HPC just suddenly came in, decoupled that locomotive, and replaced it with a bullet train engine while it was still moving.
That's actually a really perfect analogy.
Right, because we are moving from an era where silicon development was funded by a billion people upgrading their phones to an era where it is funded by, like, a handful of hyperscalers.
Yeah, these massive tech giants building million GPU data centers.
And that transition is accelerating, right? It's not just standard AI anymore.
No, and that's a key distinction. It's accelerating specifically because of the evolution from generative AI to agentic AI.
Agentic AI. Explain the difference for the listener, because that's huge.
Okay, so we are no longer just dealing with models that require massive upfront training runs and then just sit relatively idle until you type a prompt into them.
Right, like the old chatbots where you ask a question and it answers.
Exactly. Agentic AI involves autonomous systems that are continuously running. They are constantly evaluating data, executing multi-step tasks across completely different software environments.
They talk to each other too, right?
Yes, communicating with other agents. It is this persistent background intelligence.
So it's always on.
Always on. And the continuous inference compute required to support millions of autonomous agents operating simultaneously. It requires silicon at a scale, density, and power efficiency that legacy architectures just simply cannot support.
It fundamentally changes the economic engine of the industry.
How so?
Well, for years, the assumption was that a slowdown in consumer spending on electronics would drag the semiconductor foundries down with it.
Right, people buy fewer laptops, fab revenue drops.
Exactly. And the update specifically noted that consumer and price-sensitive end markets are currently facing severe headwinds. Macroeconomic uncertainties, inflation, rising component prices.
Yeah, nobody is upgrading every year anymore.
People are holding onto their phones for 3, sometimes 4 years now.
Totally.
Yet the foundry's revenue is exploding upward by 37%.
It's completely counterintuitive.
The AI megatrend has completely decoupled the leading-edge semiconductor business from the general consumer business cycle.
And that decoupling is forcing a massive reallocation of capital. I mean, think about it. Generating nearly $46 billion in a single quarter requires infrastructure that does not currently exist.
You literally have to build the future to make that money.
Exactly. The physical reality of printing microscopic transistors on silicon wafers at the volumes required by these AI hyperscalers, it demands capital expenditures that rival the GDP of entire nations.
The CapEx numbers are insane. Let's get into the CapEx megaton.
Yeah, so this update confirmed that they are raising their full year 2026 capital expenditure budget to a range of $60 billion to $64 billion.
Just for 1 year.
1 year.
And the breakdown of that $64 billion is really heavily skewed toward the absolute frontier of manufacturing, right?
Oh, overwhelmingly. Between 70 and 80% of it is going directly into advanced process technologies.
So we're talking about the 2-nanometer node and below.
Exactly. Which means buying entire fleets of those extreme ultraviolet lithography machines from ASML.
The ones that cost hundreds of millions each.
Right. And then constructing the incredibly specialized clean rooms to actually house them.
What about the rest of the budget?
Another 10% goes to specialty technologies, and the remaining 10 to 20% is earmarked for advanced packaging, testing, and mask making.
Advanced packaging has been a huge bottleneck, hasn't it?
Yeah, it's been the primary bottleneck in getting these massive AI accelerators actually shipped out the door.
But honestly, even that massive global CapEx number was completely overshadowed by their announcement regarding the U.S.
The Arizona announcement, yeah.
Yeah. They announced an additional $100 billion investment.
Just massive.
Specifically for their Arizona operations, targeting the construction of several more logic wafer fabs. I think it was roughly 4 more facilities in total.
Yeah, about 4 more mega fabs. And these will be entirely dedicated to 2-nanometer and below technologies alongside local advanced packaging capabilities.
Which is wild. But this raises a fundamental question, I think, of geopolitics and logistics.
Oh, for sure.
Like, why commit an additional $100 billion to a region and desert that completely lacks the established, hyper-efficient supplier ecosystem of Taiwan?
Well, it comes down to a convergence of very intense pressures.
Right.
First, there is the multi-year structural demand from the AI megatrend itself, which is backed by firm top-down and bottom-up data from the cloud service providers.
They know the demand is there.
Right. But more importantly, there is just unrelenting pressure from major U.S. tech companies and the U.S. government itself to secure the leading-edge supply chain geographically.
Ah, right. The hyperscalers are betting their entire corporate futures on AI right now.
Literally their entire existence. And they cannot afford a single point of failure in the Taiwan Strait.
It's just too risky for them.
Way too risky. Furthermore, you have the reality of inflation hitting the specialized equipment really, really hard.
I was wondering about that. Does inflation hit semiconductor tools the same way it hits groceries?
No, it operates on a completely different scale. The materials, the specialized construction for those vibration-proof fab floors we talked about, and the lithography tools themselves, they're experiencing hyperinflation due to their own supply chain constraints.
No.
So when a next-generation high-NA EUV tool costs upward of $350 million,
Jesus.
right? A 5 or 10% inflationary increase on that translates to massive nominal dollar requirements.
You're suddenly adding tens of millions of dollars per machine.
Exactly. And the crucial context here is the lead time.
You can't just build this overnight.
No, you cannot spin up a 2-nanometer fab in a year. It takes years of planning. The $100 billion they are committing to Arizona today is securing capacity for the projected realities of 2030 and beyond.
Okay, but I have to push back on this. I really have to challenge the certainty of those projections.
Okay, let's hear it.
Committing over $160 billion globally based on current AI demand models. That feels like an astronomical risk to me.
It is a massive bet.
Because right now, sure, the cloud providers are in an arms race. They are buying every piece of advanced silicon they can get their hands on. But capital expenditure cycles in the tech industry are historically boom and bust,
Always have been.
What if we reach, say, 2028, and these hyperscalers realize they have vastly overbuilt their AI data centers relative to the actual software revenue they're bringing in?
That is the big fear.
They will slash their orders immediately.
Yeah.
So doesn't this $100 billion desert expansion leave the foundry highly vulnerable to holding the most expensive empty real estate in human history?
It's a great point. It is the defining financial tightrope of the 21st century, honestly.
Did management address that risk?
They did. They directly addressed it during the update. They acknowledged that while they view agentic AI as a fundamental, permanent new industry, macroeconomic cycles will still exist.
Okay, so they aren't totally blind to it.
No, but they argue that the foundry has a structural visibility advantage.
What does that mean?
Well, because a 2-nanometer AI accelerator takes roughly 5 years to co-develop, they are not just relying on abstract market research or analyst guesses.
Oh, they actually see the design?
Yes. They are looking at the literal silicon blueprints and the hard financial commitments that their customers are finalizing right now for 2028 and 2029 deployments.
So they have the receipts, basically.
Exactly. The hyperscalers are essentially underwriting this expansion. But, your point about risk is totally valid, and it actually manifests immediately on their balance sheet.
Right, because of the margins.
Yeah. Expanding into the desert and rushing the 2-nanometer node carries a profound, immediate penalty on the company's profitability.
That brings us to what I call the profitability tug of war, the cost of the bleeding edge.
It's brutal.
Because despite projecting nearly $46 billion in revenue for Q3, their gross margins are actually expected to drop by 1.7 percentage points.
Landing at a midpoint of 66%.
Right. And a significant portion of that margin compression is driven by the steep ramp-up of the 2-nanometer technology.
Just bringing it online hurts them.
Yeah, just bringing 2-nanometer into high-volume production is projected to dilute their gross margins by 3 to 4 percentage points in the second half of the year.
We really have to examine the financial mechanics of a semiconductor foundry to understand this, because on the surface, it makes no sense.
Right. Why does producing the world's most advanced, most expensive product actually destroy your profit margins in the short term?
It comes down to yields and depreciation. When you transition to a microscopic next-generation node like 2-nanometer, your initial defect density is extremely high.
So a lot of the chips are broken.
Exactly. The yields, meaning the percentage of perfectly functioning chips on a single silicon wafer, are much lower than they will be, say, 3 years from now.
So you are essentially throwing away a significant amount of highly processed, incredibly expensive silicon as you refine the manufacturing recipe.
Yes, it's a very expensive learning curve. And simultaneously, the depreciation of that multi-billion-dollar equipment hits your accounting books immediately.
Right, the capital intensity is just wild. It's like, I was thinking about it like a gym membership.
A gym membership.
Yeah, hear me out. It's like paying for a 5-year ultra-premium gym membership all on day one in cash.
Okay, I see where you're going.
Your bank account looks terrible today. The margin dilution is huge.
Yeah.
But you have to start depreciating that $350 million machine on day one, even if you are only getting a few usable chips out of it.
Right. The upfront burden is staggering.
But it's the only way you get the results you want in the future. And the overseas expansion only compounds that margin compression. Right?
Oh, absolutely. The Arizona build-out dilutes margins by another 2 to 3% in the early stages.
And didn't the update say it actually gets worse?
Yeah, it noted that this dilution will actually widen to 3 to 4% in the later stages of construction.
Why does going overseas hurt the margins so much?
Well, the overseas dilution is a direct result of operating outside their native ecosystem.
In Taiwan.
Right. In Hsinchu, or Tainan, the foundry is surrounded by this deeply entrenched, highly dense network of chemical suppliers, tool maintenance contractors, and just specialized labor.
Everything is right there.
Exactly. If a critical component fails, the replacement part and the expert engineer are a 15-minute drive away.
But in Arizona,
Replicating that in Arizona requires importing talent. It requires establishing entirely new supply chains for ultra-pure chemicals and navigating a significantly different labor and regulatory environment.
which takes time and money.
So much money. You are absorbing immense inefficiencies, which drags down your profitability even when the final product commands a huge premium price.
It is the ultimate test of long-term capital allocation.
Truly.
You are deliberately sabotaging your near-term financial metrics to secure a monopoly on the future. I mean, you generate immense free cash flow from your older, fully depreciated nodes, like the 5-nanometer and 3-nanometer lines that are currently just printing money.
They really are.
And you immediately incinerate that cash in the Arizona desert to build the capacity for 2030.
Because you have to.
Yeah, you take the financial hit today because it is the only physical way to manufacture the structures required for the next decade of AI.
And the structures they are preparing to manufacture push the absolute boundaries of material science.
Let's talk about that roadmap. Because if 2-nanometer is eating into margins now, what is coming next?
The labs are already moving way past 2-nanometer. The update provided a highly detailed roadmap out to 2029, and they introduced the A14 family.
A14, and that represents their 1.4-nanometer equivalent, right?
Exactly. A14 is scheduled for pre-production in 2027 and high-volume production in 2028.
So fast.
And this node represents their second generation utilizing nanosheet transistors, which is a fundamental architectural departure from the FinFET designs that have powered the industry for like the last decade.
We really need to explain this part clearly. Why is that transition from FinFET to nanosheets or gate-all-around technology, why is it absolutely mandatory at these atomic scales?
Okay, so for years, the FinFET design worked perfectly. You know, this little fin of silicon sticking up, and you drape the gate over 3 sides of it to control the flow of electrons through the fin.
Sounds simple enough.
But as we get down to the 2-nanometer and 1.4-nanometer level, the physical dimensions of that fin become so unimaginably small that quantum mechanics starts ruining the classical physics.
Literally quantum physics getting in the way.
Specifically, quantum tunneling.
What happens there?
When the gate regulating the current becomes only a few atoms thick, electrons begin to randomly phase through the barrier even when the transistor is technically switched off.
Goes leaking.
Massive power leakage. And in a data center containing billions of transistors, that leakage manifests as uncontrollable heat.
Which requires more power to cool down.
Exactly, creating this cascading failure in energy efficiency. So, nanosheet transistors solve this by abandoning the fin entirely.
They just get rid of it.
Yeah. Instead, they slice the silicon into these infinitesimally thin ribbons or sheets and stack them vertically.
Okay.
The gate then surrounds these ribbons on all 4 sides.
Oh, I see. You completely encase the channel, giving the gate total electrostatic control over the electron flow.
Yes, which violently shuts down that leakage.
And the performance metrics they shared for this A14 nanosheet architecture are heavily tailored for the AI data center, aren't they?
very heavily. Compared to the 2-nanometer node, A14 offers 10 to 15% faster speeds at the exact same power consumption.
Right.
Or, and this is crucial, if you lock the speed to the 2-nanometer baseline, A14 delivers 25 to 30% power savings.
Wow.
It also provides a 20% gain in pure logic density.
That 30% power saving is, in my opinion, the most critical number in the entire update.
I agree completely. Power is currently the absolute limiting factor for artificial intelligence.
Yeah, we are literally reaching the point where utility grids cannot physically deliver enough electricity to specific geographic locations to run these next-generation AI clusters.
We're hearing about data centers trying to secure their own nuclear reactors.
Exactly. So a 30% reduction in power consumption at the transistor level. That is the difference between an AI model scaling to the next parameter tier or just hitting a hard thermodynamic wall.
It buys them time.
But the engineering roadmap goes even further than A14, right?
Oh, yeah. For 2029, they announced the A13 and A12 nodes, which introduce entirely new mechanisms for scaling.
Let's look at A13 first. It features what they are calling a 97% optical shrink, yielding a 6% die area saving.
Right.
We need to be clear about what an optical shrink actually implies for the listener. They are not changing the fundamental transistor architecture from A14, right?
No, the architecture stays the same.
Instead, they are pushing the extreme ultraviolet lithography tools to their absolute resolving limits,
Yes.
using the lasers to carve the exact same A14 circuit patterns, but universally scaled down by 3% in every single dimension.
Exactly. And while a 6% overall area reduction sounds, kind of marginal,
So tiny.
it does. But in the context of a highly expensive, massive AI silicon die-like a reticle limit AI accelerator, that 6% means you extract more functional chips from a single 300-millimeter wafer.
So it drives down the unit cost significantly.
Very significantly. Furthermore, because the components are physically closer together, the electrical signals have a shorter distance to travel, which marginally improves speed and reduces interconnect capacitance.
Every little bit helps at that scale.
Right. But the true architectural revolution arrives with the A12 node.
Oh, this is the part that blew my mind. The A12 node introduces super power rail technology.
Super power rail or backside power delivery network. It completely changes how a chip is physically laid out.
I was trying to visualize this, and I look at it through the lens of city planning.
Okay, let's do the analogy.
If you imagine a leading-edge AI chip as this hyper-dense metropolis like Manhattan,
Sure.
historically, all the power lines delivering electricity and all the data routing pathways, they were all built on the surface of the city, tangled together in this massive, congested grid.
Just a mess of wires on top.
Exactly.
Yeah.
And as you try to push more data traffic through the city, the power lines are physically blocking the routes.
Right.
So what the A14 nanosheet does is make the individual buildings taller and highly efficient, improving density.
That tracks. But eventually, the congestion of the power delivery network itself becomes the bottleneck, right?
Exactly.
Because the electrons have to travel through 15 or 20 layers of microscopic metal wiring just to reach the transistor at the very bottom.
And losing voltage the whole way.
Yes, what we call IR drop, and generating heat every single step of the way.
Exactly. So what A12 superpower rail does is essentially rip up the entire electrical grid and bury it deep underground.
They are physically moving the power delivery to the backside of the silicon wafer.
Which is insane to think about. Now, the surface of the chip is entirely cleared out. It's dedicated 100% to high-speed data routing.
Right.
You pump the electricity up from the bottom directly into the transistors, and you pull the data out from the top. It completely eliminates the routing congestion.
The manufacturing complexity required to execute that backside power delivery is staggering.
How do they even do it?
It requires polishing the silicon wafer down to a fraction of its original thickness.
Wow.
Then utilizing these nano-through-silicon vias to perfectly align the power rails on the back with the microscopic transistors on the front.
It is a masterclass in precision engineering.
It really is. And management noted that customers are currently finalizing their designs, locking in the blueprints for these advanced nodes, well ahead of schedule.
Because they need them so badly.
Exactly. They predict that A14, because it hits this optimal equilibrium of performance, power, and area scaling, will become a long-lasting workhorse node for the industry.
Kind of like how their 5-nanometer node anchored the last generation of hardware.
Very similar. Yeah.
You know, we spend so much time discussing these atomic scale miracles.
The flashy stuff.
Yeah. The nanosheets, the backside power delivery, the multi-billion-dollar clean rooms. It paints a picture of an industry entirely focused on the bleeding edge. But the reality of an AI data center is far more complex and heavily reliant on technology that is, frankly, decades old.
And this is a huge point.
Because an AI cluster isn't just made of 3-nanometer logic chips. It requires an entire ecosystem of supporting components.
And this is where we see a fascinating vulnerability in the global supply chain.
Yeah, the CEO was highly specific in this update. He classified artificial intelligence not just as an application trend, but as a new industry entirely.
He compared it to the dawn of the automotive sector, didn't he?
He did. He said it will integrate into absolutely everything. But a $40,000 AI accelerator chip cannot function in isolation.
It needs friends.
It requires a symphony of supporting silicon, specifically power management ICs or PMICs and CMOS image sensors.
Right. Let's talk about power management. A modern AI GPU draws over 1,000 watts of power.
It's basically a space heater.
Truly. And when that chip suddenly executes a massive calculation, it demands a violent, instantaneous spike in electrical current.
If the voltage fluctuates by even a fraction of a volt, or if the current isn't delivered in the exact microsecond it's requested, the entire system crashes.
Completely stalls out.
The PMIC is the regulator that manages that brutal transient power demand.
And then you have the CMO image sensors, which act as the sensory organs for AI.
Right, for robotics and cars.
Exactly. Allowing autonomous robotics in vehicles to actually perceive their physical environment and feed that data back into the computational models.
And here is the critical point for the listener. Neither PMICs nor CMOS image sensors are manufactured on 2-nanometer or 3-nanometer nodes.
No, not at all.
They are built on mature legacy technologies. We're talking often 90-nanometer or 0.18 micron processes that were cutting edge 20 years ago.
Which means the market has completely bifurcated.
Explain that.
Well, the general demand for mature node chips used in basic consumer electronics like smart home appliances or cheap microcontrollers, that demand remains incredibly weak due to the macroeconomic environment.
People aren't buying as many smart fridges.
Right. However, any mature node capacity that is qualified for the AI ecosystem is facing severe structural shortages.
So we have a situation where a multi-million-dollar AI server rack simply cannot be shipped because it is waiting on a 50-cent power management chip.
Exactly. The entire bleeding-edge revolution is bottlenecked by a shortage of decades-old technology.
Which raises a massive strategic question regarding competition.
I know where you're going with this.
Like, if you are a competing foundry and you are bleeding billions of dollars trying to master the physics of 2-nanometer and just failing to get your yields up.
Yeah.
Why not pivot? Why not surrender the leading edge, buy up depreciated equipment, and aggressively target the severe shortage in AI-qualified mature nodes?
It makes a logical sense on paper.
Right. Why don't competitors steal the market share at the foundation of the ecosystem?
It seems like an obvious arbitrage opportunity. Yeah. But it fundamentally misunderstands the engineering reality of high-performance mature nodes.
Oh, really?
Yeah. Manufacturing a PMIC for a television remote is simple. But manufacturing a customized, multi-phase PMIC designed to regulate the extreme thermal and electrical demands of a liquid-cooled AI supercomputer, that requires a deeply specialized variant of a mature process.
It's not just off-the-shelf stuff.
No, typically it's a BCD process, which integrates bipolar, CMOS, and DMOS technologies all onto a single chip.
So you can't just flip a switch on a 90-nanometer machine and start printing AI-grade power controllers.
Exactly. You can't. The dominant foundry has spent 2 decades co-optimizing these specific mature processes directly with the hyperscalers and the chip designers.
So they have the secret recipe.
The intellectual property and the manufacturing recipes are highly, highly customized. Furthermore, the massive AI customers do not want a fragmented supply chain.
Oh, they want a one-stop shop.
Right. They demand a holistic manufacturing partner who can produce the 2-nanometer logic chip, the mature node power management chip, and the specialized memory controllers, and guarantee that they all meet perfectly interoperable specifications.
Which brings us directly to the competitive moat, and why this specific foundry seems to operate with almost impunity despite massive geopolitical efforts to fund alternatives.
The subsidies are huge everywhere else.
Right. The U.S. government is heavily subsidizing domestic competitors. Korean foundries are pouring billions into advanced packaging alternatives, like Intel's EMBT technology rising up.
Everyone is trying to catch up.
But when an analyst asked the CEO about the threat of customers defecting to these heavily funded rivals, his response was highly dismissive.
It was almost funny.
He stated that choosing a foundry partner is not like buying milk from 7-Eleven.
That 7-Eleven analogy perfectly encapsulates the switching costs in this industry.
Break it down.
Well, if you go to a convenience store for a specific brand of milk and it's sold out, or a competitor's brand is on sale, you simply grab the alternative.
Right.
The product is a commodity, the transaction is instantaneous, and the outcome is identical. You still get milk. Semiconductor manufacturing is the exact antithesis of a commodity market. When a hyperscaler or a major chip designer chooses a foundry, they are essentially co-investing in a 5-year marriage.
I love that. The switching costs are practically insurmountable. I actually break this defensive moat down into 3 interconnected pillars:
What are they?
technology leadership, manufacturing culture, and customer trust.
Let's hear them.
On the technology front, as we saw with the A14 and A12 roadmap, they are consistently, predictably, hitting their physics milestones.
Clapwork.
If you are an AI company, your entire valuation is based on delivering the next generation of performance on time.
NVIDIA has to hit their targets.
Exactly. If you move to a competitor because they offer a cheaper wafer price, and that competitor delays the node by 8 months because of a yield issue, your product is obsolete before it even launches.
The cost of delay in AI is existential.
Right. And that ties directly into the second pillar, doesn't it?
Manufacturing culture, yes, because proving a transistor works in an R&D laboratory is entirely different from manufacturing 10 million of them a month with 99.9% reliability across a global network of fabs.
Anyone can make one chip in a lab.
Right. The institutional knowledge required to identify a microscopic contaminant in a chemical supply line or to optimize the throughput of an EUV scanner. You just can't easily replicate that simply by spending government subsidies.
Throwing money at it doesn't create culture.
No, it requires a deeply ingrained generational culture of precision execution.
And the third pillar is customer trust, which is built on the timeline of co-design.
The 5-year marriage.
Right. A customer doesn't just email a digital blueprint to the fab and wait for the chips to arrive in the mail. The customer's silicon architects and the foundry's process engineers are working side by side years before production begins.
They're actively tweaking the physical layout of the logic gates to perfectly accommodate the specific idiosyncrasies and optical limitations of that exact foundry's equipment.
So by the time that chip is ready for high-volume manufacturing, the IP is so intimately intertwined with the specific fab process that porting it to a competitor would require starting from scratch.
Exactly. It's not buying milk.
No. It's co-owning the dairy farm. You can't just abandon a farm you spent 5 years building because the neighbor's grass looks slightly greener today.
That's a great extension of the analogy. And honestly, we haven't even touched on the ultimate lock-in mechanism.
What's that?
Which is no longer the silicon itself, but how the silicon is packaged.
Ah, advanced packaging.
Advanced packaging has moved from a back-end afterthought to the primary frontier of architectural innovation. As these AI clusters scale up, moving massive amounts of data horizontally across a circuit board using traditional electrical copper wires, it generates way too much heat and introduces way too much latency.
The physics of electrons moving through copper simply can't keep up with the data demands anymore.
It's too slow.
Yeah.
Which is why the transition to silicon photonics moving data using light is becoming absolutely mandatory.
Oh, lasers.
Yeah. The update highlighted their key UP technology, the Compact Universal Photonic Engine. They are integrating laser optics directly alongside the silicon logic.
Just putting the laser right on the chip.
Right on the chip. And the engineering required to seamlessly bond a photonic engine to a 2-nanometer logic die. I mean, you have to manage the thermal coefficients of expansion so the alignment of the lasers doesn't drift by a single micron under intense heat.
Because if it shifts, the light misses the target.
Exactly. And that is heavily proprietary. Because this foundry is pioneering these mandatory, ultra-dense packaging technologies like CoWoS and CuPe, in parallel with the silicon nodes, the customers are entirely captured by the holistic ecosystem.
So you cannot take your 2-nanometer design to a competitor if that competitor doesn't possess the proprietary packaging required to attach the optical interconnects that your architecture relies on.
You're completely locked in.
Wow. When you look at the totality of this update, from the $45.8 billion revenue projection to the $100 billion desert expansion, down to the quantum mechanics of nanosheets and the integration of silicon photonics,
It's a lot to take in.
you are looking at a single company that is single-handedly constructing the physical infrastructure of the next economic epoch.
Yeah.
They are deliberately absorbing massive near-term margin compression and taking on unprecedented logistical risks because they recognize that agentic AI is a structural shift on par with the Industrial Revolution.
They are literally building the factories that will build the mines of the future.
That's a profound way to look at it.
But, there is a profound philosophical and economic question embedded in this immense capital cycle, and it is something you, as the listener, should really consider as we conclude our analysis today.
Leave us with a final thought.
The foundry is executing this $160 billion global expansion based on the current projections of human engineers and executives, right? They are attempting to forecast the computational requirements of 2029 and 2030.
So they are assuming a linear or perhaps steadily exponential curve of demand based on current AI architectures.
Precisely. But the fundamental nature of agentic AI is autonomy and self-improvement.
Right.
We are rapidly approaching the threshold where AI systems will begin actively optimizing their own algorithms. They'll be rewriting their own code bases and identifying new, exponentially more complex domains to compute.
They will accelerate the technological cycle far beyond human pacing.
Exactly. So the question becomes, how reliable are human projections of compute demand when the primary consumer of that compute is an autonomous intelligence?
Oh, wow.
Are we looking at a $100 billion overbuild in the desert? Or, terrifyingly, is this unprecedented expenditure actually a massive underestimation of what autonomous AI will ultimately demand?
If the AI starts generating its own demand for compute, outstripping our ability to physically build the fabs,
Yeah.
that is a physical bottleneck we may not be able to solve with just capital. Thank you so much for tuning into the Quarterly Call. For more episodes, please remember to rate and follow our show. Until next time, stay curious and stay informed.